Hello, everyone. This is Doug Kothe from Oak Ridge National Lab, and I'm pleased to be able to give an Exascale computing project update. Thanks to Earl, Steve, Bob, and the gang for giving me a chance to give everyone an update. Just a reminder, we've been able to brief the HPC user forum a number of times about ECP. ECP is in its 5th year of a 7 or 8 year project, and we have 3 technical focus areas: application development, software technology, and hardware and integration. I'm going to touch briefly on activities since we last spoke here. I guess that was in May. I'll briefly touch on applications and software and spend a little bit more time on the hardware and integration focus area in terms of an update. So as a reminder, the DOE HPC roadmap is here for Exascale systems. You see systems deployed at the 6 DOE labs with pre-Exascale as well as Exascale. The Exascale era is upon us with the Frontier and the Aurora systems really coming in. And the Perlmutter system, I believe Katie Antipas is going to talk about. It's being going through acceptance and being deployed as we speak. So it's an exciting time, really important time for ECP with hardware really on the horizon. To date, we've really only had NVIDIA GPUs. They're fantastic hardware, having great experience as I've noted on Summit. But of course, with the Exascale systems and Perlmutter, we have 3 different types of GPUs. That's both challenging and exciting to have a very diverse ecosystem of what we'll call accelerated nodes. So I'll say a little bit more about what we're doing with regard to these systems. I showed this slide last time. Just a reminder, one can go out and find at the DOE Oscar website the specs of Frontier and Aurora. There are also much more information at the websites given there below. These are multiple GPU systems, very exciting systems, a lot of local compute and local memory, so very beefy, fat nodes, as I would call it, on these systems. So really, real exciting developments that we've been working hard to prepare for. I can say a little bit about what we've been doing. We're certainly not just waiting for the Aurora and Capitan and Frontier systems to come before we have first experience on hardware. We've been working really for the past 2 years on early access hardware, and it's shown here with various diamonds representing when we had access to certain systems. Here we are really today, almost at the end of Q4 for FY fiscal year 21. So that's, the kind of present is really between FY 21 and 22. We've had a lot of experience already on early hardware at Frontier known as Tulip and its upgrade, and Aurora systems known as Iris and Yarrow. In particular, we're focusing on systems at Aurora called Arcticus and Frontier, or the ALCF known as Spock. You can see that really we start off with single node functionality tests. Can we compile and get the right answer? Then we move more towards single node performance testing, compiling, debugging, and now we're getting more, as we move forward, getting more into the software and the slingshot interconnect. So each early hardware system, early access system, test and development system has kind of its own purpose for our specific needs. Just to give you an example, we've been spending a fair amount of time these past several months on the Arcticus system at ALCF and the Spock system at OLCF. The speeds and feeds are shown there, but basically we have 17 nodes with the Intel XeHP GPU, and what's listed there is a software environment, the kinds of support we've been enjoying. Similarly at Spock at the OLCF, we have 12 nodes there with an AMD EPYC CPU and 4 MI100 GPUs, so we get a lot of ground truth, so to speak, with regard to the latest hardware we can get our hands on in the software environment. Shown there at the bottom is kind of how we've been tracking usage and access. All of our teams, both apps and software, are getting experiences, not surprisingly, finding issues, features we need or bugs we need fixed. And so this has allowed to a lot of interaction with our vendors, in this case, Intel, HPE, and AMD. Just as a reminder, our application efforts been ongoing. We have 24 first mover applications shown here. A lot of good progress there. Again, our starting point was pretty daunting. The 24 projects comprise 78 different codes, millions of lines of code, tens of millions of lines of code, and really supporting broad user communities. The current status, each app has its own development plans. Each app is making a lot of progress. We're really pleased. We feel very confident about our ability to show that they can meet their challenge problems that they signed up to at Exascale, as well as order half the applications really have to show they are meeting at least 50x performance science work rate performance improvement relative to 2016. Andrew Siegel at Argonne National Lab has put this slide together. He leads our application area. I really like this because it kind of shows what ECP is focusing on, demonstrating challenge problem, the ability to do challenge problems, testing and demonstrate new capabilities, performing performance porting to Exascale, targeting really new science capabilities. So it's just not a porting exercise. And then post-ECP is really making sure that these tremendous science tools are ready for production science simulations, further validation, further exercising. Our expectation of these applications will be science and engineering tools for not years, but for decades to come. So that sort of shows the handoff post-ECP. And porting to moving to these new architectures is not just porting code, which of course implies rewrite, profile, optimize, do things like loop ordering, memory coalescing, kernel flattening, but adapting numerics. And that really means rhythmic changes, thinking about things like reducing synchronization, trying to exploit reduced precision, avoid communication where you can, try to do as much compute local, and adapt our physical models, the mathematical representation, maybe you would say with particles as opposed to meshing, doing on-the-fly recomputing versus lookup tables, really prioritizing what models go in where. So certainly thinking about the GPUs and the accelerated node is a true co-design effort, not just for software, but for the numerics and the physical models themselves. We really have great hope and, frankly, expectation that many of our applications, maybe all of them, will meet their figure of merit performance improvement. That's a 50x improvement since 2016. You can see on the Summit system, measured and extrapolated a full system just on Summit, we have really good early returns. This is not on the Exascale system, so the proof's in the pudding when we get there. But early indications are these are the 11 applications on the hook, so to speak, for 50x performance, and many are seeing not just 50, but up to 200, which is incredible. So we're very, very optimistic that we're really on the right track, and the experiences on Summit should carry over to Aurora, Frontier, El Capitan, etc. Some application development highlights, just quickly, and this will be these slides will be left behind. So here you see some highlights for our power grid application, for our Center for Particle Applications, which is a co-design effort, and our wind plant flow physics modeling. So on the power flow side, we've got a new release of ExaPF. It's a power flow solver for GPUs. Really, the exciting thing there is that the package supports an entire tool chain for reduced space optimization method. This area really requires discrete algebraic equations and optimizing there, sometimes even mixed integer programming. So really going to high-level optimization, scalable optimization is very important for the power grid application. For Kothe, the release of a new library it's not a new, but a new version of Cabana, which is a particle kinematics library for pushing particles, mapping particles to meshes to particles. Now they've been able to show that they can not only run on AMD GPUs, but also the Intel GPUs. So being able to use Cocos with a sickle backend, they've been able to really show that all the features of the Cabana library are now available on the Intel GPUs, and demonstrate that with a couple of proxy apps. In the wind application, the real challenge is sparse linear solvers, both strong and weak scaling. And they've found that an interesting combination of algebraic and geometric multigrid for preconditioners is important, and piggyback on what the AMRX software framework has been done. So here are the challenges: solver development, and that's been really, really well received, and nice developments there. Exascale, which is data analytics at the Exascale for free electron lasers, has been targeting an MTIP, multi-tiered iterative phasing algorithm. That's really for single particle imaging. Something that was really not planned, but a nice development is to be able to recognize different types of noise, which is going to be inherently available or there in experimental images, and be able to characterize the noise and be able to recognize the noise and filter it out. So that's a great feature that's going to be needed when the linear coherent source comes up at SLAC, or at least its upgrade. The EXALT effort, molecular dynamics at Exascale, in terms of the material science effort, has been able to really target increased performance, in this case on the V100 processors, of order 30x since the beginning of ECP on just the machine learned potential known as SNAP. That's been a nice development I think we spoke about in the past. And the WARP-X, which is advanced particle physics accelerators or modeling thereof. This is a good example of we're not just porting and we're not just software engineering. There's important algorithmic development efforts going on. In this case, particle beam-driven plasma wake field accelerator showing 2x speed up, combining the advantages of enhanced stability by using nodal pick methods and staggered pick methods. Really interesting development. So an eclectic mix of algorithmic, computer science, computational science efforts in the software and the application area. The software technology area, we've talked about it in the past, has 6 technical areas: programming models, runtimes, dev tools, math libraries, data and viz, and packaging it all together in the software ecosystem, as well as the NSA software stack. Just as a reminder, we're packaging these products in terms of software development kits or SDKs. And the order half dozen SDKs have been embodied in our extreme scale scientific software stack, E4S. The latest release is May 2021, has ordered 76 distinct products. So we're very excited about this development. The releases are coming out early and often. Every 3 months seems to be the cadence now. Samir Shinde at the University of Oregon leads this effort. It's really been an exciting development. There you see the website. Go check it out. The latest release is there from just in May. 76 full release products, version 24.05. And as I noted in the previous slide, not just ECP developments, but community AI and ML frameworks such as PyTorch, TensorFlow, Horovod, and a number of different containerized or build on build on raw metal. Our co-design efforts are now there. AMRX, Cabana, and MFEM. This group will be expanding as we move forward. Encourage you to go check out this website. There's tutorials and documentation there. So we have a really broad strategic vision for E4S, well beyond ECP. We think it's emerged as a top-level component in the HPC user community. We've been interacting with other agencies, with industry and international collaborators. We're expanding into new domains for us, ML and AI, as well as lower level components at the OS level and more. We are seeing that E4S is providing better, faster, cheaper deployment, and we think it's a springboard for the software stack of the future. In fact, we're in the process of drafting a strategic plan over the next decade, and there'll be more to come there. But suffice it to say, it's just not evolution of the current products and in E4S, but we'll see expansion into key emerging areas such as AI for science, edge, and quantum. Some software technology highlights here, just very, very briefly. Encourage you to go check out our website for more here. The SICM effort, Simplified Interface to Complex Memory, led out of Los Alamos, has really guided data management in Nalu Wind, which is an unstructured parallel solver for Wind. The analysis shows some significant potential for increasing throughput on heterogeneous memory systems. And basically on-node memory, but we have it at the CPU level, the GPU level. We also have non-volatile memory, so lots of hierarchies there, in addition to level 1, level 2 cache. So lots of complexities. Really, SICM is helping apps being able to maximize exploiting this area. Probably the most mature SDK in ECP is the math libraries known as XSDK for ECP. Had its second release of examples and a tremendous suite of math libraries that are being contributed to, not just from ECP, but from other communities. Encourage folks to go take a look there. That's our most mature area. The Slate sub-team, Jack Dongera's efforts, part of the Clover effort, recently added ROCm AMD GPU support for its latest releases of the Slate and BLAS++ linear algebra libraries. So we continue to release early and often with new capabilities. The Argo project out of Argonne has some nice new developments, which is a lower level thread-based resource management for OS and runtime. Released its UMAP version 2.1.0. Please go take a look. The Solve effort was a very, very important effort for us, led out of Brookhaven Lab for scaling OpenMP within LLVM. Released its latest runtime library known as Bolt, and it addressed internode scalability bottlenecks and MPI interoperability issues. Some nice efforts there. And the Hyper team, we brought it into ECP since we started, a really key multi-grid effort led out of Lawrence Livermore. They've recently added HIP support for AMD GPUs on unstructured solvers, continue to push on algebraic multi-grid, and I think further in the future we'll probably start to bring in some geometric multi-grid efforts that various codes are working on. Some other highlights: MPI Forum, formally approved MPI 4.0, major new features that ECP Teams had a role in making sure were part of that effort. Were championed by the OpenMPI effort. So needless to say, we're doing development efforts, but also have an active seat at the table in these international standards. We stood up a new effort recently, which was to really focus on Cocos in a new project known as Sake, Solver and Kernels for Exascale. Here the focus is on Cocos and Coco kernel for AMD and SYCL. So a new version of 3.4 of the Cocos kernel library was released. The Alpine effort, Jim Ahrens is a champion here at Los Alamos. Algorithms and infrastructure for in situ viz. It includes often on-the-fly compression algorithms, in this case ZFP out of Livermore. Released a new version for Lagrangian in situ reduction, a 3x speed up on Summit. Really important for a number of codes, in particular the NIX code and astrophysics code and SW4 and earthquake wave code have used this latest capability. Let me just say now a little bit in the last 5 or 10 minutes about the hardware and integration area. Here I'm going to use a few slides from Katie Antipis, who's our lead here. She gave a recent talk at the Oscar Advisory Committee ASCAC meeting that I thought were just great. So here are some key faces. Katie and Susan Coughlin are our leads and deputy leads respectively. Katie's been responsible for a number of system deployments at Lawrence Berkeley, and Susan is on point for the Aurora system. So we're really lucky to have this great set of leads. And this really is, as I noted before, let me go back, responsible for hardware integrations and evaluation, app integration, software deployment, and training and outreach. And boy, oh boy, has this become critical for ECP as we begin to move into productization and deployment. So recent activities, they've been working the early hardware access with our leadership computing facilities. What we call application integration are performance engineers at facilities that are often domain scientists, but could be computer scientists, computational scientists. We're deploying them on application teams. They're making great efforts, great strides in making sure that the application efforts really reflect the latest and greatest with regard to deployment on the latest hardware. In the interest of time, all this focus on the app int effort and the software deployment effort. So the software deployment effort is really has made tremendous progress the last year and a half, really responsible for taking the E4S product portfolio, 76 products now, and making sure that we have set up seamless, automated, continuous integration, that the latest E4S efforts are available on not just pre-Exascale systems like Summit and Perlmutter, but early access hardware and ultimately the Exascale hardware. So 18 months later, under the leadership of Ryan Adamson at Oak Ridge, we're leveraging the E4S software stack and packaging to significantly simplifying testing, deployment, and continuous integration. We built pipelines with CI deployed at each facility on production systems, including the GPU architectures. The software testing on early hardware, access hardware has begun with CI deployed. And there you see below, just a few months ago, we only have 67 products in E4S, and so now we're up to 76. But we're really the goal is every product in E4S has test suites defined, SPAC tests defined, and those tests are being deployed and used as part of CI. And so while we have some work to do, we're real excited about the progress there, being able to do real-time development on E4S and productization and deployment and testing all at the same time. App integration is really taking our matching applications with facility readiness efforts, and this really distills down to really a group of talented individuals who know the hardware and also know the applications. So the goal is really 21 of our 24, the 21 open applications being deployed and performant on Aurora and Frontier. Scott Parker and Balint Jew are leading the efforts, overseeing the overall effort with Chris Knight, Stephen Nichols, and Debbie Bard on point for making sure we're targeting appropriate efforts at Aurora, Frontier, and Debbie Bard. And I'd be remiss not to show this eye chart of the app teams, a lot of talented people that ECP is funding through facilities that are deployed on the various applications. And apologies here for the acronyms, but there you see the names of folks at various facilities, ALCF, OLCF, and NERSC being deployed onto the application teams in ECP. This is a best practice that our facilities at the Department of Energy Oscar shop have used for the last decade. ECP, not surprisingly, of drafting this approach. We're using it and scaling it up for all of our apps. So again, what do? They engage with vendor experts, apps teams, facility performance staffs, implement algorithms on new architectures, optimize applications, implement new programming models. So they're embedded with facilities staff. They're also matrix on the apps teams. You know, we monitor their progress pretty closely, and boy, oh boy, this is really paying off. Let me give you 3 quick examples here. Games, which is the goal here, led by Mark Gordon at Ohio State, is enable quantum chemistry on extremely large-scale systems of interest in catalysis and energy research. Here, the model is a Fortran-based code with OpenMP, and you see the efforts by Colleen Bertoni porting a molar per set electron correlation integral, and you see the progress made from progressive optimizations from OpenMP threading to porting to MKL, offloading to GPUs, restructuring the loops. Now you see you might step back a little bit in performance, enabling concurrent CPU plus GPU computation, and you see the speed up is quite remarkable. It's not necessarily monotonic, but really targeting a key compute-intensive part of games, and great progress being made here by Colleen. The ExaBiome effort, led by Kothe at UC Berkeley, is a very unique and non-traditional Exascale application for metagenomic assembly. In this case, answering questions like how do microbes affect disease and growth of switchgrass, or what happens to microbes after a wildfire. Really, the challenge problem here is to find species, genes, and relative abundance in microbial communities. There are stretch goals for each of our apps here listed here. The bottom line is metagenome assembly is really, really hard problem just in and of itself, but even harder to scale up on to implement on GPUs and to scale up on Exascale systems. The key app in this case is an app known as MetaHitMer, Metagenomic Sequence Assembly for short reads. You can see the various stages here, from Kamer histograms to contig generation, to alignment, assembly, scaffolding. So, you know, a really difficult problem, distributed hash tables, graph algorithms, and other discrete algorithms. And there you see on the right, progress being made in terms of runtime reduction as we scale up. So Kothe and her team have done a tremendous job here. And in particular, a couple of folks listed there at NERSC that have really targeted the local assembler model for MetaHitMer. In this case, performance improvement on GPUs really requires low-level intrinsics, making the code somewhat NVIDIA specific. So now working to port to SYCL for Intel and HIP for AMD requires there's some differences in intrinsics. And these codes rely greatly on integer performance. For that reason, instruction roofline is used frequently for performance deep dives, or working closely with vendors. Shown here on the right is the relative runtime between CPU and GPU, and you see that the timing is going down as it should, and you also see their scaling challenges. So basically, the bottom line is MetaHIP pipeline has improved performance up to 42% on 62 nodes. That's not bad at all. In fact, that's very, very good. The local assembly portion has been reduced from 34% to 6.3%. So a lot of effort on local assembly. It's such new and novel effort that, not surprisingly, this has been accepted SC21. It's nominated for a Best Paper Award. The last example is another computational chemistry effort known as NWChemEx. In this case, NWChem has been a really important computational chemistry code for a couple of decades for the community. The ECP is supporting moving this effort to Exascale. There are a couple of different challenge problems targeted here: the efficient production of biomass and the efficient conversion of biomass to biofuels. One of the focuses of their challenge problem is a catalyst known as zeolite, shown there. It's a promising promising candidate for conversion of biomass-derived alcohols to more useful hydrocarbons, and really complicated effort. NWChem is has both software goals and computational chemistry goal. The overall goal is sufficient use to pre-exascale and exascale computing technologies for chemical science research and certain targeted challenge problems that I mentioned. In particular, the couple cluster models really don't scale very well, and the challenge is to get them to scale better. Reduce dependent on highly accurate electronic structure methods on molecular system sizes. The scaling goes like into the 7th often, so the target is to reduce that exponent 7 to 6 or 5 or even less. So a lot of redesign and reimplementation going on here, moving a Fortran code slowly to a C++ code base, targeting Hartree-Fox, CCSD, and embedded DEFT. So there you see a lot of effort led by Teresa Windus at Ames, and it's a redesigned, improved version of the NWChem code, as I mentioned there. A key underlying effort here is what's known as the TAM. These are basically, there's a lot of tensor algebra going on here, so to be able to isolate and localize that effort in terms of the TAM module has been really key. That's been developed under ECP. It offloads tensor operations to appropriate backend. So by isolating the tensor algebra, now you can focus on the compute-intensive efforts, first on NVIDIA, now moving to AMD and also Intel. So the couple of clusters, single and doubles, which again scales in a really complicated way, they've been able to achieve speed ups of over 40 recently, and moving from Titan to Summit to NWChemEx. So a real promising effort there. This is a very complicated code with a lot of things moving parts, and so it's really been exciting to see that development. So again, I think we're very much on track for achieving our objectives. Just to summarize, in the application development area, I've said this in the past, results on Summit have consistently exceeded expectations. Early access hardware has been instrumental for us to understand how what we've done on Summit can move over to AMD and Intel, and for the most part, we have not been caught off guard or have not had surprises there. The teams have really shown a keen awareness as what is needed. Often the algorithmic restructuring and data structures for NVIDIA's have carried straightforward over for these other GPUs, and we're on track. I think I've shown that on some slides in previous. Software technology, we do have a working testing framework. E4S continues to evolve. The 76 products now available in E4S in the May release all have a direct line of sight to our applications. So we're building a requirements-driven software stack that's going to, I think, live for not years, but decades to come. And most importantly for this presentation, the hardware and integration effort, which is the last mile in testing and integrating and pushing these products and apps on the hardware, both pre-Exascale, early access, and Exascale hardware, is really working well. So I encourage folks to check out our website, look at these slides. Feel free to contact me or any of our team. Moving forward, we're in a really kind of a penultimate time as we get on early hardware. It's an exciting kind of year ahead for us as we get access to Frontier and Aurora. Be real excited in the months and in the next few meetings to share a lot more of our results. That said, I'll conclude my presentation, and really excited at time for ECP, and hope to interact with the HPC user forum community in the future. Thanks.